Hello everyone, welcome back to the final GIS lecture video of this module, where I want to go through some examples of matrix multiplication. And the first one I actually want to go through is I want to actually go through this idea of the row vector times the column vector that we did before, but I want to flip it, because we said that U times V gave us a 1 by 1 matrix, which is a single number, and that was sort of the foundation of all of the matrix multiplication that's come before it. But now I want to flip it. I want to say, what do we get if we multiply a column vector times a row vector? Okay, so let's go ahead and give ourselves a little bit more room here. I'm going to sort of reach over here and just quickly write down the numbers. U equals 1, 2, 3, and V equals 2, negative 2, 4, and 3. Okay, so now I've got them scratched over there, so I can come over here and we can write them out more thoroughly. All right, so we have U, the row vector, equaling 1, 2, 3. And then we have V, which is the column vector, equaling negative 2, 4, 3. And we've already done UV, right? We've done this. But what about VU? Right? Can we do this? Well, let's think for a second. V is a 3-row, 1-column matrix. Right? U is a 1-row, 3-column matrix. Right? So our inner dimensions match. So let's do this in green. Right, our inner dimensions are both 1, so our inner dimensions match. So our outer dimensions, 3 by 3, mean that this does indeed work, and UV is going to be a 3 by 3 matrix. Okay, but what are we actually going to put in the elements? Let's give ourselves plenty of space here. And let's think this through. So this first element, if we go back to my original example of this is now A, okay, this is now A, and this is now B. So let's just make sure we keep ourselves straight here. This is now A, and this is now B, right? We flipped it. So we think of A as being a bunch of row vectors, and we think of B as being a bunch of column vectors. Right? I'm using that last conceptual concept that I pointed out, where if we think of A as a bunch of row vectors and B as a bunch of column vectors, and then each element is going to be the row vector times the column vector of the particular location, right? Then we know, let's go ahead and redo this as negative 2, 4, and 3, just because I like to keep things clean here. 1, 2, 3. Right, so this is going to be the first row of A, which is going to be negative 2, times the first column of B, which is going to be 1. Right, so going down, this is going to be 1 and 1. Going across, this is going to be negative 2, negative 2, negative 2. Right, the second row is going to be the second row of A, which is going to be 4, 4, 4. And then the third row is going to be the third row of A, which is going to be 3, 3, 3. The second column of the output is going to be the second column of B, which is going to be 2, 2, and 2. And the third column is going to be the third, which is going to be 3, 3, 3. So if we do the math on that, we're going to get a 3 by 3 output. Negative 2 times 1 is negative 2. Negative 2 times 2 is negative 4. Negative 2 times 3 is negative 6. 4 times 1 is 4. 4 times 2 is 8. 4 times 3 is 12. 3 times 1 is 3, 3 times 2 is 6, and 3 times 3 is 9. All right, so this result right here, right, this is the result of the column vector times the row vector. Okay? So hopefully that makes sense. Let's go ahead and look at a slightly more complicated example. Let's look at this one. So we have A that is 3, 2, 1, 5, and we have B that is 6, 2, 4, 1. And we're asking ourselves, what is A times B? Okay, so I'm going to rewrite these in color-coded. So we have 3 times 2, 1, and 5. B, we have 6 and 2, 4, and 1. Okay, so these are color-coded so we know where they're coming from. Okay. So, what is A times B? Well, let's look at our dimensions, right? We have a 2 by 2 being multiplied with a 2 by 2. Do our inner dimensions match? Yes, they do. So we're good. What are the outer dimensions? Well, the outer dimensions are 2 and 2. So our result is going to be a 2 by 2 matrix. So we know that AB is going to result in a 2 by 2 output. Okay? So what do we actually put in the elements? I'm going to give myself plenty of space here. So again, the way I like to think of this, A becomes a series of row vectors and B becomes a series of column vectors. And then you think about which position you're in. So for the first row, we're taking the row vector of A, of the first row of A. So that's going to be 3 and 2. So we know we're going to have a 3 and 2 here. We know we're going to have a 3 and 2 here. For the second position, we take the second row of A. So we're going to have a 1 and a 5. And we know we're going to have a 1 and a 5. And then now we multiply those, right, the row vectors times the column vectors of B. So we're going to have a 6 and a 4, a 6 and a 4. We know we're going to have a, in the second column, we go with the second column vector of B. So that's going to be a 2 and a 1, and a 2 and a 1. And then we're adding up the results, right? Because again, we're doing the multiplication of the row vector of A times the column vector of B. Row vector of A, column vector of B. Row vector of A, column vector of B, right? That's what these things are. So if we do the math on that, okay, right, I'm skipping over a little bit. 3 times 6 is 18 plus 8. 3 times 2 is 6 plus 2. 1 times 6 is 6 plus 5 times 4 is 20. 1 times 2 is 2 plus 5. Right, I'm going to shrink this down a little bit to make it fit here. Right, 18 and 8, that's going to be 26. 6 and 2 is 8. 6 and 20 is also 26. And then 2 and 5 is 7. So that's A times B. Well, what about B times A? B times A, again, 2 by 2 times 2 by 2. Right? In this case, the dimensions are the same, so it is doable. Our output is also going to be a 2 by 2 matrix. Let's do the same thing we did before. But this time, our rows are coming from A or from B, and our columns are coming from A. So hopefully this makes sense. So in this case, right, we're going to take our rows from B. So this is going to be the first row of B. So this is going to be 6 and 2. This is still going to be the first row of B. So this is going to be 6 and 2. This is going to be the second row of B. So this is going to be 4 and 1. A little bit more space there. 4 and 1. This is going to be the second row of B. So this is also going to be 4 and 1. Okay. So now we go and look at the columns. We're just doing the columns of A. So this is going to be 3 and 1. This is going to be 3 and 1. This is going to be 2 and 5. This is going to be 2 and 5. Okay, so again, I was looking at the rows of B. So B is now a row vector. And the columns of A. So A is now our column vectors. And again, I'm just setting up the row vector times the column vector. Row vector times the column vector. And I've just switched which one I'm looking at the rows and which one I'm looking for in the columns. Okay, hopefully that makes sense. I don't want you to get lost. Okay, so let's do the math. 6 times 3 is 18. 2 times 1 is 2. 4 times 3 is 12. 1 times 1 is 1. 6 times 2 is 12. 2 times 5 is 10. 4 times 2 is 8. 1 times 5 is 5. So if we do that, again, I'm going to shrink this down just a little bit. All right, that's 20. That's 22. That's 13. And that's 13 as well. So this right here is the result for B times A. And you'll notice that these are not the same. Let me do that in red. Right, these things are not the same. Multiplication, and I said this before, matrix multiplication is not commutative. Let me write that down. Right, matrix multiplication is not commutative. Right, A times B does not equal B times A. So we're actually going to have one more example, but I want to stop here because I know this was a lot. So I encourage you to pause the video, go back, rewatch the example, and as always, please reach out. Thank you.